Okay, welcome to lecture here. Get started here in just a sec. We are starting chapter 16, I think. Again, the notes should be up online if you need them. Okay, so the good news sort of is we are now kind of going past the, I would say, probably the most difficult part of the class for most people. Again, those last two chapters, which, as you know, has a lot of stuff in there. Usually, again, are the ones that give people sort of the hardest time. We're now going to sort of move into some more stuff that's a little bit more straightforward, I guess, in that sense. More like kind of pick the right formulas and plug and chug type of thing in there. Again, you still obviously need to understand what's going on, but it's a little bit more sort of, like I said, picking the right formulas and sort of putting things in. So not so much conceptual, if you will. Still, obviously, you need to understand what's going on, but a little bit more kind of focused in that. So we're going to talk about entropy, free energy, and equilibrium in this chapter. This is sort of a continuation, if you will, from some things from Chem 50, for example. In Chem 50, we also will see in this chapter some of our old favorites, like delta H, for example. Delta H, if you remember, hopefully is the enthalpy. Let's spell that right. Enthalpy. And that's basically the heat of a chemical reaction. And a lot of times we look at this in terms of the energy and what type of reaction we're dealing with. Again, if we have a delta H value that is negative, that typically is a exothermic reaction. If we have a delta H that's positive, that is typically an endothermic reaction. Exothermic meaning heated energy is released, right? Endothermic meaning obviously heated energy is absorbed. And so delta H is energy, and energy really is what is sometimes referred to as the first law of thermodynamics, that conservation of energy. And the rest of these guys here that we'll talk about in this chapter here is delta S, which is the entropy, not to be confused with the enthalpy. Free energy, which is delta G. So we're going to use some of the other alphabet here, some letters in the alphabet other than K. But of course, we will go back to K at the end here because we miss K. It's in everything we do. But we will see some other things. So a lot of this is going to be more about thermodynamics. And a lot of what we'll talk about revolves whether or not, for example, a reaction occurs spontaneous. And we'll talk a little bit more about sort of what spontaneous means here in this chapter as well. So let's talk about some spontaneous type processes here. And these are all spontaneous processes, some of these physical and chemical type processes. Obviously, water runs down a hill. If you take some sugar, it'll dissolve in a cup of coffee at 0 degrees Celsius at 1 atmosphere. And that's when we see ice freeze or melt. Again, that's sort of the change of state that occurs between, say, solid and liquid, which would be more of a physical type process. When heat does sort of flow, it does always go from sort of the hotter object to the colder object. So it travels from hot to cold. And as a gas expands in an evacuated bulb, also, there's spontaneous processes such as oxidation or reduction reactions that occur. So for example, iron will be exposed to oxygen. You pretty much just need some oxygen, a little bit of moisture, and you got everything that you pretty much need for rust to form. And those are all sort of spontaneous processes. Same thing here when we look at the guy skiing downhill. Obviously, that's a spontaneous process. He pretty much just needs to go over the hill, and he's going to spontaneously go down. Going up the hill, obviously, is a non-spontaneous process and probably not what this guy wants to see as he's coming down the hill. But obviously, to get yourself back up the hill, you need to kind of work to get yourself to the top. And as we'll see in this chapter and also the next chapter as well, we can make sort of non-spontaneous reactions occur by applying some extra work or energy to do those type of things. So it's also really important when we think about spontaneous reactions. And again, sometimes when we think about, or we say, hey, a reaction is spontaneous, sometimes we misunderstand what that means. Sometimes we think about it in the sense that, oh, it's spontaneous, so boom, it's going to happen super fast. And it really doesn't mean that. So when we talk about a reaction in this chapter, or just in general as being spontaneous or being really non-spontaneous, is another way. What we're really referring to is not really how fast or slow a reaction is occurring. We're talking about the conditions under which this reaction is happening. Under those particular conditions, if a reaction is spontaneous, we would expect it to basically occur. Could occur really fast, could occur really slow, just going to occur. And that's really what spontaneous means. Again, it has nothing really to do with how fast or slow the reaction occurs. It just means that it will occur. When we talk about how fast or slow a reaction occurs, that's what we talked about at the very beginning of the semester. That's what we talked about with kinetics. So kinetics deals with how fast or slow a reaction occurs. Thermodynamics, which is what we're dealing with in this chapter, really talks about whether or not a reaction will actually take place. And again, that's really what we mean when we say something is spontaneous. Again, sometimes people get sort of the wrong understanding of that, and they think that if a reaction is spontaneous, it's going to occur like really, really fast. And again, it does not necessarily mean that. It could occur fast, but it could also occur really slow. So for example, the formation of ammonia, NH3, that is a spontaneous reaction, but it's actually a very slow reaction if you don't put a catalyst in there. So even though it does occur very slowly. Any questions on that there? So here's a couple other things here, and I don't know how well it's coming through on yours. There's actually these gas molecules are actually in a couple of tubes. And again, there's sort of a valve over here. And in a spontaneous process, if we open the valve, we would expect those gas molecules to kind of flow into that empty space and sort of fill it here in a spontaneous process. If we started with sort of this container here, which is on both sides, and we had gas molecules on both sides, and again, if we open sort of the valve, we wouldn't expect all the gas molecules basically to head over to the left-hand side spontaneously. You could help it along, maybe heating this side up may force those guys to the other side, but spontaneously, we wouldn't expect all those guys just to end up on the left-hand side. So this again would be considered a non-spontaneous type process. So this brings us to, and also a really important understanding here is, we talk about delta H and we talk about enthalpy and the heat of a reaction. So does a reaction being exothermic, for example, does that mean that we will have a spontaneous reaction occur? So if we look at some of these reactions here, these are all spontaneous reactions. We have a combustion reaction here of methane. Delta H is minus 890, which is exothermic. We have the formation of water here. Also a negative delta H, which means these guys here are exothermic. We also have a solid going to liquid, which is basically an ice cube melting. And that is also a spontaneous process. We know if you just take an ice cube out of the freezer, it will pick up all the heat and energy from the surrounding and it will start to melt. But that is actually an endothermic process here with a delta H as positive, along here with dissolving an ionic compound like ammonium nitrate. Again, here a positive delta H. So these guys are endothermic. So what we see here is we do see all these things are spontaneous. We do see that some of them are exothermic and some of them are actually endothermic. So looking just solely at the delta H or the enthalpy for a reaction does not necessarily always guarantee that we will have a spontaneous reaction. So sometimes we think, hey, if we have a negative delta H, it's exothermic, it's always going to be spontaneous. Or if we have a positive delta H, it's endothermic, it probably would not be so spontaneous. But here, this shows you that you can have spontaneous reactions where the delta H is positive or the delta H is negative. So exothermicity does really favor spontaneity. Again, you have a lot of sort of excess energy, if you will, because we're going to give off the energy. But it doesn't necessarily guarantee it. As we can see with the last two examples there, we do have a couple reactions that are positive in terms of their delta H and endothermic. So we do have to look at sort of another sort of factor to help us decide whether or not a reaction will be spontaneous or not. And one of those other sort of thermodynamic properties that we look at is what is known as entropy. And entropy is abbreviated with a delta S. So delta S stands for the change in entropy. So what is entropy? Entropy really is a measure of disorder or randomness that we find in a system. And actually, unlike a lot of other sort of thermodynamic values, as the amount of disorder increases, the amount of entropy also increases. So the more disorder, the more randomness you have, the more craziness you have, the higher the entropy value will be. And vice versa, the more order you have, the more things are really together, not flying around crazy. We have a lot more order happening. We see a decrease in entropy. And one of the things that are a little bit different with delta S is if the delta S is positive, that means that we see an increase in the disorder. So the more disorder we have, the more positive the delta S value becomes. And the more order we have, the more negative that the delta S value becomes. So the more order that we have. So sometimes, you might want to choose which way you want to think about these things. You want to think about these things in terms of order, either more order or less order, or do you want to think about it in terms of disorder, more disorder or less disorder? Again, the more disorder, the more craziness, the more positive our delta S value will be. The more order, the less randomness that's happening, the more negative our delta S value will basically occur. And what we're talking about is in terms of sort of final state compared to its initial state. So when we think about a chemical reaction, we have our reactants that go to products. And essentially here, our reactants are our initial. And our products are essentially our final state. And that's why, for example, you're probably familiar with as well for something like delta H. We usually will, one way to calculate it is to take the products minus the reactants. And the really reason you're doing that is because the products are your final state and your reactants are your initial state. So you're basically taking your final state minus your initial state when you do those, like delta H equals the sum of the products minus the sum of the reactants. You're basically taking the difference from where it started to basically where it ended. And again, that tells you, again, overall what's sort of happening in a chemical reaction. Now, when we think about sort of states for substances, we could relate it to entropy as well. If you just think about sort of our three states, we have solid, where pretty much everybody's packed in pretty tight to each other. And that means that there's a lot of order that's happening in that sense. In the liquid state, still packed in relatively tight to each other, but a little bit more room for movement, which is why obviously liquids are fluid. And obviously when we get to the gas state, nobody is packed into each other, they're flying around. So obviously when we hit the gas state, there's a lot of disorder happening, right? We got a lot of molecules flying around, moving around, creating a lot of disorder. In the solid state, everybody's kind of stuck there together, pretty tight to each other in a pretty ordered fashion, especially when we deal with something, for example, like ionic solids, as you probably learned in Chem 50 as well. Ionic solids basically have long range order. So when they come together, all the positive cations and negative anions, they really do arrange themselves in such a way that it creates this really repeatable pattern. Perhaps you remember from Chem 50, you talked about things like unit cells and sort of how those things come together. So especially with ionic solids, we have really that long range of order. So in terms of states, we can look at our states in terms of entropy and have an idea of what's happening. If we have something in the solid state, that's a lot of order. It should have a low entropy value, and that means that the entropy value will probably be more negative. While if we have something in the gas state, that is something where there's a lot of disorder as things are flying around, and that means that the entropy value would be more positive. And we would have an increase in entropy if we went from solid to gas. We would be going from a more ordered state to a more disordered state. And again, we would expect the delta S to be positive as you go that way. Opposite if you're sort of heading this way, we go from a gas state where we have a lot of things flying around really crazily to a state where we get to solid, not so many gas molecules flying around, we would expect a decrease in the entropy value, and it would become more negative in that sense. Any questions on that? So when we talk about sort of disorder, it is related to probability. And as we can see here in this example, before we get there, and I scribbled on it, I believe that is that's water going from solid to liquid. Again, we would expect a delta S here to be positive. Going from solid state to liquid, a lot more disorder happening. Positive delta S should occur. So disorder is related to really probability, and a probable event is one in where there is a lot of ways that it could occur. While if we have sort of an improbable event, you know, there's only one way that can happen, or a few ways that can happen. So in an ordered state, there's a low probability of occurring, and it has typically a small entropy. In a disordered state, there's a high probability of that occurring, and we have usually a larger entropy. So the old saying is like, you know, there's many different ways that you can kind of screw something up and do it wrong, right? There's a lot of chance that somebody will do something wrong. But, you know, there's kind of only one way or a few ways that you could do something correct, or the correct way of doing things. And again, that's why entropy deals with the increase in disorder, because, you know, there's a lot of ways that things can go wrong, right, or mess up, and a lot of disorder can occur. One sort of mathematical relationship to this is what's sometimes referred to as the Boltzmann Equation. And that's what we see here in the box. We have S, which is our entropy, is equal to K, and K is the Boltzmann constant, which is on the bottom here, times the natural log of W. W is what is sometimes referred to as microstates, and microstates are basically different ways you could sort of accomplish something, or do something, or perform something. Now, when we think about, for example, the box that we got here, or these circles, when we look at something like this, we have 4 circles, and we have basically several different boxes, or 2 boxes. And if we wanted to put all 4 circles in one box, there's really only one way to do that. You'll either put it on the left-hand side, really, or the right-hand side, which is the same thing. So there's only one way that you can do that. So the number of microstates would be 1. Now, if I wanted to put 1 circle in one box and 3 in the other, there's actually 4 different ways you could sort of accomplish that. And the microstates would be 4. If I want to put 2 circles in each box, there's actually 6 different ways that could occur. Now, because we have, say down here, only one way for that to occur, the entropy would be very small. And we just put it into our Boltzmann equation. If we take S is equal to K times the natural log of 1, natural log of 1 is 0, which means S is equal to 0. So you get a very small value for S, as opposed to here, if you did like the natural log of 6, you get something like 1.76, which obviously gives you a more positive number as you come into our delta S here, or our S in this particular case. So in this case here, since there's a lot of different ways that you can basically accomplish this, by putting 2 and 2, which is about 6 different ways, it's a pretty high probability that you would be able to do that. Kind of like a carnival game, right? If you only had to put 2 balls in one side, you'd have it out of 4, you might have a pretty good chance of winning something. If you had the rigged carnival game where you got to put all 4 sort of balls in one side of the hole, you might not get them all in there, right? So it's probably improbable that that would occur. So here in our 2 and 2 situation here, where we have a high number of ways of doing that, we have a high entropy, and it's probably pretty probable that that would occur. As opposed to where we want to put everybody into one side, there's only really one way to do that. You got to be kind of perfect to do that, and it's going to have a low entropy and a lower probability of occurring. So again, here K is that number that's on the bottom, and it is a constant, and W is the number of microstates. Any questions on that there? So what we're looking at here is a number of processes where it does lead to an increase in the entropy, or the delta S becomes more positive. So some of these we talked about, again here, things in their solid state, very ordered. Here as we go to liquid, again, still relatively ordered, but obviously as you can see here, a little bit more room of things moving around. So we increase more disorder happening here in comparison of going from solid to liquid. So again, we would expect the delta S to be positive. And then obviously as we go from our liquid to our gas phase, we can see that everybody has pretty much broken apart from each other. They're flying around, and we would expect an increase in the entropy as well. Actually making a solution causes a great increase in entropy in both the solute and the solvent. So as you remember, hopefully a solution is made up of two things. It is made up of the solute, which is the smaller part, and it's made up of the solvent, which is the larger part of the solution. And in the case of the solute here, we pretty much got to break everybody apart to allow it to dissolve. So we're causing a lot of disorder in the actual solute itself. In the solvent, for example, if we have water, right? We have a bunch of waters there. They are hydrogen bonded to each other. So in order to allow ions to come in, we have to kind of break apart some of these waters so that they could go around and surround all of the ions as we dissolve it. So we're also creating a lot of disorder in the solvent part, and thus we see a very big sort of increase in entropy for both the solute and the solvent in this case. There's a lot more disorder happening here, a lot more ions floating around in the solution that wasn't there before, a lot more of the water molecules breaking apart from each other and associating with ions that weren't there before as well. So we see a very big sort of increase in the entropy as we do that. Temperature as well is another way that we could cause a lot more sort of entropy to occur, especially if we increase the temperature. So obviously when we increase the temperature, we're creating a lot more energy. When things have more energy, they are moving more, especially say gas molecules are moving a lot. If it's a solid, it has a lot more energy to sort of break apart and maybe go into the liquid phase. So providing all that extra heat and energy by raising the temperature typically causes a lot more disorder to occur. Again, like that old saying, light a fire underneath somebody, right? They start to move a lot more than they would. Same idea here. As we obviously increase the temperature, everybody's gaining more energy. More energy means that they're moving around more. In that sense, they have a lot more energy and a lot more disorders happening from where it's a lower temperature where they don't have as much energy. So they're just kind of maintaining, if you will, sort of where they're at. So as we increase the temperature here, going from a lower temperature to a higher temperature, we would expect, again, an increase in that entropy value. Any questions on that there? All right, here. So here's a few examples here. So take a minute here or two and try to determine in the system of each of these, is the entropy change increasing or decreasing? So take a look at those and we'll talk about them here in just a second. Okay, so let's take a look here. So first off, condensing water vapor. So when we go through condensing or condensation, that is the process where we go from gas back to liquid. So gas state, they are flying around crazily, if you will, a lot of energy moving around. When we get to the liquid state, they kind of lost a lot of energy and no longer can kind of escape each other, and they kind of go into the liquid phase. That means we're going from a more disorder to a more ordered state. And we would expect that the randomness decreases. And that would mean that the entropy value would be negative in this case, right? So we would expect a lot more order. The delta S value would become more negative in this case as this happens. When we form a sucrose crystal from a supersaturated solution, so the idea here is the crystal part. So typically when you form a crystal, that's a solid state. That's a pretty good solid state. And usually in those cases, you have a lot more order happening, right? Again, in the solid state, things are going to be more ordered. And forming a crystal is a pretty ordered sort of arrangement. That also means that the entropy should be decreasing. And the delta S should be negative here as well. Again, we're going from a more disorder in a solution to a more ordered crystal or solid type situation here. So we would expect a delta S to be negative. Heating hydrogen gas from 60 to 80. So we're still staying in the gas phase here, but by increasing that temperature, we would expect the velocity of that gas to be more, and it will start flying around a lot faster, and that should cause a lot more disorder, right? So disorder will increase here. And that means our delta S should be a positive number in this particular case. And lastly, sublimation there. So sublimation, again, a reminder, is the process where we go from solid directly to gas. We skip the whole liquid part. So obviously we're going from solid, which is more order, to gas, which is more disorder. And again, that would increase the amount of disorder. And we would expect our delta S to also be positive in this particular case. Any questions on any of those there? Okay, so entropy is a state function, and just a reminder what sort of state functions are. You probably talked about them again in Chem 50, but state functions are basically properties that are really determined by sort of two properties, if you will. Basically, where you started and where you ended. So really, it doesn't really matter sort of how you got there, what path you took to get there. The only real difference or the importance is, again, sort of the position at which you started and the position at which you ended. So energy is a state function. Enthalpy, which is delta H, is a state function. Pressure, volume, temperature, and entropy as well are state functions. Now, for example, here, if we look at these two hikers, they both started here, and they both really ended here. And in terms of their potential energy, they really have the same potential energy, but they did take different paths. So the blue guy took the more direct route up the hill. The red guy took the more scenic route around the hill to get to the top. But really, in terms of their potential energy, the only difference is their final state here from their initial state. And this is really the idea behind things that you probably have done before, if you remember everybody's favorite thing, which is Hess's law. And then remember, Hess's law is when you basically take a bunch of different reactions and you add them together to get an overall reaction, and you could adjust the delta H values to do that. And the principle behind that is this, that, you know, if a reaction takes 1 step, 2 steps, 4 steps, 5 steps, the overall energy difference is really just where you ended and where you started. So you could basically add up all those individual steps and figure out how much energy you had going on. And that gets you really your difference from where you started to where you ended. And that's the same idea here. So when we look at entropy, a couple of things that are different than, say, enthalpy is you will have to look up some delta S values in a table. And typically, if you look up the delta S values in tables, there's a couple really different things than, say, delta H values that you look up in the table. First off is really units. So for example, the units of delta H, when you look them up, say in a table, are typically kilojoules per mole. The units of delta S are typically joules per mole. So this is really important because later in this chapter, we will see a formula or an equation that uses both of those together. And if you don't do a conversion, you are going to be off by like a factor of 1,000. So that's a very common place where people sometimes mess up in terms of these units. Other things that are also slightly different in terms of, say, delta H and delta S when you look them up in a table or look for a table value. If you remember, anything sort of in a standard state, things like O2, H2, a metal, and stuff like that, for delta H, we'll typically have a value of 0. Different though for things that are delta S, you will actually find values for those things. So hard to see on my screen, but I think that is H2 there or something like that. So you'll find some values actually for those things in their natural states. So that's also something very different. So normally delta H, anything, you know, like H2, O2 in this sort of natural uncombined state, usually we think of it as having a 0 for its delta H value. But for delta S, which is our entropy, you will actually see a value for those things. And lastly, the other kind of main difference as well is, for the most part, when you look up your delta S values in the tables, they are typically positive numbers. So for our delta H, we have negative and positive numbers, but for delta S, it is typically positive numbers. So there's a lot of things you got to watch out for in this chapter, and especially when we start using a lot of these thermodynamic terms together and formulas. Units are a big thing. Again, typically people kind of mess up on that. They end up being off by a factor of 1,000 because of the units. So you do want to make sure that you watch out for that. Any questions on that there? By the way, we also sometimes see, you know, when we look at some of these thermodynamic values like delta H naught, delta S naught, we'll see delta G naught. So we'll sometimes see these knots or little circles kind of written above things. And that usually means, for the most part, sort of standard conditions. And when we talk about standard conditions, what we're talking about is usually the pressure is 1 atmosphere for dealing with gases. The temperature is 25 degrees Celsius. These are typically what we sometimes refer to as sort of table values. So most table values that you look up, say in the back of the book or in some other source, these are usually sort of the standard conditions we talk about. If it's something to do with concentration, it's 1 molar. So a lot of times when you see that, that's usually like those little knots, standard conditions, sort of table type conditions, again, meaning that the pressure is usually 1 atmosphere. If you're dealing with a gas, the molarity is usually 1 molar. Temperature is usually like 25 degrees Celsius. So these are sort of our standard conditions. I think we'll see it a little bit later on as well, but that's usually what we sort of anticipate. And that's usually what those little sort of knots mean when you see it, is sort of this was done under natural or standard type conditions. So as I mentioned before, the first law of thermodynamics is probably that one that you talked about in 50 with delta H, which is energy. And it is basically that energy can be converted from one form to the next, but we don't gain or lose energy along the way. So there's always that sort of conservation of energy. And that is the first law of thermodynamics. And again, you probably saw that when you talked about sort of energy transferring from one place to the next. So if something loses a certain amount of energy, something else gains a certain amount of energy, and vice versa. And usually what we deal with when we talk about thermodynamics are 2 things, which is the system. The system is pretty much anything that you're dealing with. So in the laboratory, for example, if you're doing a reaction in the beaker, that's your system. If you're doing like in a test tube, that's your system. Everything else is what is known as the surroundings. And when we talk about sort of flow of something like energy, for example, if the system lost 5 kilojoules of energy, the surroundings would gain 5 kilojoules of energy, and vice versa. If the surroundings like lost 5 kilojoules of energy, the system would then gain it. The only difference is in terms of something like energy, the way we represent sort of that flow of energy is with the sign. So typically negative signs means that it's exothermic, so something's losing that amount of energy. And if something's gaining that amount of energy, they usually have the positive value of it, which represents that it's endothermic and they're absorbing that amount of energy. The second law of thermodynamics is sort of what we're talking about now. And the second law of thermodynamics deals with entropy. And again, says that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So if we have a spontaneous process, in order for us to sort of determine that it's spontaneous using delta S, we do have to calculate actually something that is known as the delta S of the universe. So the delta S of the universe is equal to basically those two things, the delta S of the system plus the delta S of the surroundings. So by looking at these two things and adding them together, if we add it up and we actually do calculate the delta S of the surroundings, the delta S of the universe, and it is positive, then we know that that reaction is spontaneous. Again, if we calculate the delta S of the universe and it's negative, it would be a non-spontaneous process. Again, a spontaneous process meaning that it doesn't occur necessarily fast or slow. It just means that that reaction is expected to basically occur under those conditions. If we calculate delta S of the universe and it equals 0, we are at an equilibrium process. And that means an equilibrium process, like we talked about, as soon as you go one way, you go the other way. There's really no net change that's sort of happening here. We don't expect a reaction to occur. Everything's kind of flowing back and forth at the same rate. So this brings up an important thing. If you want to use delta S to figure out whether or not a reaction is spontaneous or not, you do need to calculate the delta S of the universe. So we're going to talk about how to calculate these guys here in just a second, but you do need to kind of calculate each of those, add them together, and then determine whether or not the reaction is spontaneous or not. So let's take a look here. We'll start with the system. And like I said before, usually the system, is the reaction that you're doing. So a lot of times, sometimes people will say the delta S of the reaction or the delta S of the system. Again, sometimes in thermodynamics, reaction and system, again, are sometimes used interchangeable because what you are dealing with is basically your system, which is usually the reaction that's taking place. So in general, much like delta H, the way that we could calculate the delta S of the reaction or the system is basically just take the delta S of all of our products minus the delta S of all of our reactants. And we do the same thing as we've done, or you've done with delta H as well. You do need to take the coefficients into account from the balanced equation, and you need to multiply them by that. So where do we find these numbers? This is basically a table number. So we would go to the table, we would look up the value of the delta S values for each of those guys, and we would again to add up all of our products with their coefficients and subtract it from all of our reactants with their coefficients. And again, that is products minus reactants. So ultimately, that's what we've been talking about. That is our final state minus our initial state. So products are final state, reactants are initial state, and that's going to get through there. Another important thing in terms of looking up things in tables that you're probably aware of, but just to remind you, you want to always make sure that you look it up, not only for the substance that you're looking for, but you also want to make sure that you find it in its right state. So a lot of these thermodynamic tables will have multiple values for the same substance, and the main difference is the states that they're in. So you don't want to look up, say, for example, something like water, and you don't want to grab it, say, in the gas state if you want it in the liquid state, or if you want it in the solid state, because you may find, obviously, several different values for those guys depending on their state. So really important when you look it up that you do both the substance and also the correct state. All right, so why don't you take a second here. These are the values that you would find from the table here. And why don't you calculate the delta S for this system or this reaction and see what you come up with. So take a moment or two and do that. Okay, so let's take a look here. Let's take a look here in C. So again, we would find these values. Obviously, if they were not given to you, you would find them in a table. And we basically want to find the delta S, which again will be our delta S of our products minus the delta S of our reactants. So on our product side here, we have 2 CO2. So our delta S here would equal 2 times the value of CO2 that we would find in the table, which looks like 213.6 joules. We then would subtract it from our reactant. So we have 2 times the CO value, which was 197.9. Plus our O2, and again, different than delta H, you will find, as you can see here, a value for something like O2 in the table, and that would be 205 joules. And if we do all that good stuff there, let's see. We got 2 times 213.6 minus 2 times 197.9 plus a 205. Looks like we do end up with something like minus 173, excuse me, minus 173.6 joules per mole. First off, any questions on that calculation there? Now, what does that number mean? Well, that number means that this reaction, we have a negative value for delta S of the reaction, and that means that we do see that the entropy is decreasing. So we're creating more order. Now, something that you can oftentimes do in thermodynamics type problems, and sometimes you're asked to do this, is you could just look at the reaction and basically make a pretty good guess as to what you expect your answer to be. So what I mean by that is if we actually look at the reaction, before we even actually picked up the pen to do the actual calculation, if we looked at this reaction and we look on the reactant side, we actually have 3 gas molecules. 2 here and 1 here. On the product side, we have 2 gas molecules, which is obviously these guys here. By just looking at the actual reaction, we see that we're going from 3 gas molecules basically flying around crazy to only 2 gas molecules flying around. So we are decreasing the amount of gas molecules that are flying around, and thus we are actually creating more order. There's not so much crazy gas molecules flying around, there's less of them, creates a more ordered situation. So we actually could have predicted this negative sign here. So that's a good way that you can, make sure you didn't kind of mess up on your calculation or something like that. We can definitely look at a reaction, and based on, for example, how many gas molecules are made, how many gas molecules are consumed, where we start with and where we end up with in terms of the reaction, we can make a good prediction in terms of the delta S of the reaction, in terms of the sign that we should get. Should it be a negative value? Should it be a positive value? And as you can see here, as we decrease the amount of gas molecules, we created more order. By creating more order, we would expect the delta S value to become more negative. So these are good things to think about as you're doing these calculations. These are good ways that you could literally predict, not the number per se, but the actual sort of sign of it to verify that you did the calculation correctly. So we could do that here again. A couple of ways to help us with that is pretty much if we look at gases, for example, in a reaction, and if a reaction produces more gas molecules than it consumes, so basically our products would end up with more gas molecules on the product side than what we started with, we will have an increase in disorder. So we'll have a lot more gas molecules flying around. The delta S would become more positive. If we have the total gas number, the total molecules of gas decrease, we will see what we saw in the last example. We will see an increase in order, a decrease in disorder, and we would see a negative delta S. If there's really no net change in terms of gas molecules on either side, then the delta S may be positive or it may be negative, but it typically will be a more smaller number in that case. So again, we could literally look at a reaction and make a pretty good prediction. So why don't you do that for this one on the bottom, just based on the reaction, not calculating anything. Would you expect a delta S to be positive or negative in this case? So take a second here and take a look at it and see what you come up with. Okay, so if we just were to look at this on the left-hand side here, if we were just looking at gas molecules, we have a grand total of 1 gas molecule. By the way, it is this guy here. That is a solid. On the product side, we have a grand total of no gas molecules. Again, this is also a solid here. So in this particular case, we went from 1 gas molecule flying around to none, nothing flying around, right? Unlike that one fly that keeps flying by your face, right? And then when he's gone, you're happy, right? Not so much disorder happening in front of you. So we've now gone to a place of more order. So the order increases, the disorder decreases. And that means that our delta S should be a negative value in this particular case. Again, if we were to calculate it with the actual numbers, that is what we should actually see. Any questions on that? And again, if we were to calculate it, we would do products minus reactants. We would look up these values in a table and basically calculate our delta S of our reaction. Any questions on delta S of the system, which is the reaction, basically products minus reactants, look up the values in the table, And again, you can look at the reaction and predict whether or not the reaction is increasing or decreasing in terms of disorder. Let me be really clear though, by just looking at the delta S of the system like we are doing here, or the reaction, it does not tell us if the reaction is spontaneous or not. So what we're doing here, specifically right at this point, really does not necessarily give you an indication of is that reaction spontaneous or not. What it does tell you is simply this reaction is creating more disorder or this reaction is creating less disorder. You know, it basically gives you an idea about order or disorder, but it does not really tell you anything in terms of the reaction being spontaneous or not. Any questions on the system here? So that leaves us the surroundings to think about. And when we look at the surroundings, we're going to talk about how to calculate that. But let's first talk about sort of what is happening in each of these sort of processes here. So when we do have a exothermic reaction, that does mean that heat and energy is being given off. And as a result of that conservation of energy, as we talked about, that if somebody is giving off energy, there is something else that's going to absorb the energy. So on the left-hand side here, we have an exothermic reaction, which means happening in this flask. This flask is giving off all that heat and energy to the surroundings. And what that means is the surroundings is now going to pick up all the heat and energy from the system. And that means that everybody in the surroundings will now have a lot more energy. And when things have a lot more energy, we expect a lot more movement, for example, if we're talking about gases, and that would create a lot more disorder. So typically in our exothermic process, the resulting effect on the surroundings is we would expect the delta S to become positive for the surroundings. And that's because, again, it is picking up all that heat and energy from the system, and it's increasing its own entropy of the surroundings. Now, the opposite is sort of true in an endothermic process. So in an endothermic process, the surroundings itself is going to be losing the heat and energy. The system is going to be picking up all that heat and energy, and all that heat and energy is coming from the surroundings. And that means that the surroundings now are losing heat and energy. And when they do that, if we're thinking about just say gas molecules flying around, they're then going to start to fly around a lot slower. And it's going to create a lot more order there in the surroundings. And we would expect in that case, as we see on the bottom here, that the delta S of the surroundings will now become more negative. So there is a relationship between the delta S of the surroundings and the delta H of the system. The delta S of the surroundings, and this is the proportional sign, to the minus delta H of the system at constant pressure. And really what that means is very simple, is this. If I have my delta H of the system, or the reaction, and my delta S of the surroundings, and since delta H of the system in an exothermic process would be negative, that would mean that negative would be our positive delta S of the surroundings. Again, my delta H here would be negative in this sense. And that turns us into a positive for our delta S of the surroundings. If our delta H is an endothermic process, that means that my delta H would be endothermic. So since the delta S of the surroundings is proportional to negative delta H, that means my negative and positive would give me a negative value. So that's how we get to our negative value here. So it's basically the opposite relationship. Now, there is sort of something that we should think about, and it is, as we'll see here in the next slide as well, and it is temperature. So temperature does play an effect on whether or not we would see a big change in the entropy of the surroundings. So what I mean by that is, let's just take the exothermic example here for instance. And if my temperature of my surroundings was really high to begin with, the added energy that would come from the reaction as it goes into the surroundings probably would not make that tremendous amount of a difference. And we may not see a tremendous change in the entropy of the surroundings because it's already big to begin with. So if we have really high temperatures, for example, in the surroundings, that added energy that's coming in from the reaction may not make a tremendous amount of difference. So very simple example, I guess, for example, if you lit a match, you know, you'd put your hand next to it, not on it, right, but next to it, you could feel the heat coming off the match, right, and in room temperature. But if you lit the match, and obviously don't do any of this, but if you lit the match and you open it into an oven, or open an oven that was at like 700 degrees or 500 degrees or something like that, and you put the match in there, and you probably couldn't tell that much of difference between the match, the heat coming off of the match, and the heat from the oven to begin with. There's not that big of a change, as opposed to if you just took the match near your hand, you know, out in regular room temperature, you would feel the heat and stuff like that. So the temperature of the surroundings does make a big difference in terms of whether or not you would perhaps sort of see that difference. But if it's sort of normal temperature conditions, we do see this effect occur that the delta S of the surroundings will be opposite the sign, basically, of the delta H of the reaction. Any questions on that? So as I mentioned before, and just a second ago, you know, the temperature does play an effect. So again, if we're starting with surrounding temperatures that are really high, we're going to see an increase in entropy, but it's not going to be to the same extent than if we see that happening in sort of a normal temperature, a lower temperature situation. So we've talked about calculating delta S of our system as being the delta S of our products minus the delta S of our reactants. So to calculate the delta S of the surroundings, is that equation that we see on the bottom there. It is negative delta H of the system divided by the temperature. Temperature here does need to be in Kelvin. And again, here's our delta H in this particular case, which could be also the delta H of the reactant. This is an important equation. It does have a negative here for that relationship that we just talked about. We will see a formula later on in this chapter that looks almost like this guy, but there is no negative. So later on, I'll say it again, don't get confused. But here, if you're calculating to delta S of the surroundings, we do have the negative here, again, for that relationship that we just talked about, that sort of opposite relationship, delta H of the system divided by the temperature in Kelvin. And now we know how to calculate both things that we need, because if you put these together and you add them, that is your delta S of your universe. So to calculate the system, to the tables, products minus reactants. To calculate the surroundings, you take the delta H minus the delta H divided by the temperature in Kelvin, and you add both of those together. And at that point, if you add both of those together and you calculate the delta S of the universe, you then can determine whether or not this reaction would be spontaneous or not. Any questions on that? All right, so why don't you try one here, see what you come up with. Here's all the values I think you need. Calculate delta S of the system, the surroundings, and also figure out, is this reaction spontaneous or non-spontaneous? Take a couple minutes, see what you come up with. Again, delta S values should be on the bottom there. Okay, so let's take a look here. So we want to calculate delta S of the system and the surroundings, and we also want to predict whether or not this reaction is going to be spontaneous. So again, a couple of reminders that we just talked about are delta S of the system. Again, we're going to go to a table and find those values. We're going to take our products minus our reactants, and again, that's what these values would be found in a table. Our delta S of our surroundings minus delta H divided by T. They did give us the delta H here, and we do have the temperature given to us as well. So we do have all that information. So we're going to start with our system here. So our delta S of our system is going to be our product. So on the product side, we have two NH3s. So that's going to be 2 times 193 joules. And that should be it for our product side. And we're going to subtract that from our reactant side. And on our reactant side, we have an N2, which is 192. We're going to add that to our other reactant, which is H2. And there's, looks like, there are 3 of those guys. So 3 times 131 looks like. So 3 times 131. And if we do all that there, we will end up with, let's see here, 2 times 193 minus 192 plus 3 times 131. Altogether there, that looks like it is minus 199 joules in this particular case, would be the delta S of the system. Now, as we talked about previously, could we have predicted that sign of it? So let's talk about it here. So if we look at the reaction, we have 4 gas molecules on the reactant side. On the product side, we have 2 gas molecules. So we're going from more gas molecules to less gas molecules. And that means that we would expect the entropy to decrease because there's more order, and we would expect it to be negative for the reaction, which is what we saw. Again, that is all that number is telling us right now, that we are decreasing the disorder, increasing the order in this particular reaction. Any questions on that so far? Okay, so we're going to do our delta S of the surroundings, and that's going to be minus delta H of our reaction divided by our temperature. So our values that we have here is our delta H is 92.6 negative. So delta H negative 92.6 kilojoules. And our temperature was 25 degrees Celsius. So we do need to convert that into Kelvin. So that's like a 298 Kelvin. Now I have everything I need, so I'm going to put it in here, minus our minus 92.6. I'm going to multiply it by 1,000, and the reason I'm going to multiply it by 1,000 is that's going to convert me into joules, and that's because this guy's in joules. That way I have everybody kind of in the same units. You don't have to do that. You can leave it in kilojoules, but at some point you'll need to convert something. And we're going to divide it by 298 Kelvin. And in this particular case here, if we do that, that's 92.6 times 1,000 divided by 298, gives us something like 311 joules. Again, positive for our surroundings. Also, what we expect to happen here, again, this reaction is exothermic because of the negative. It's a regular temperature situation. So when our system gives off that energy to our surroundings, the surroundings should pick up that energy, become more disorder happening in the surroundings, and we would expect a delta S to become more positive, which is what we see happen here in our calculation. So again, you can make some of these predictions before you do the calculations, or even after you do the calculations, just to verify that your numbers are okay. And again, a reminder here, I've multiplied it by 1,000 so that they both will be in units of joules at this point. Any questions on that there? Now, the reason I did put them both into the same units is because really we want to know if this is going to be spontaneous. So we need to calculate delta S of the universe. And that is our delta S of the system plus our delta S of the surroundings. So again, this is a situation where you do need to watch units. And because I converted mine into joules, I'm okay in terms of my units. If you did not convert this into joules, you would have kilojoules here and joules here. You definitely don't want to add those numbers with one being kilojoules and one being joules. You're going to find yourself pretty far off there. So again, you definitely want to watch your units when you're doing these calculations. There's a lot of places where, again, those units can get in the way in terms of getting the right answer. So we're going to end up with 112 joules as our answer for our universe. And because our delta S of the universe here is positive, that would tell us that this reaction is going to be spontaneous. Any questions on any parts of that calculation? So again, just to recap here, our delta S of the system does not tell us if it's spontaneous or not. It does tell us if our order or disorder is happening. And we can see from our negative number that we're creating a more ordered situation. Our delta S of the surroundings also does not tell us whether or not a reaction is spontaneous or not. It just tells us, you know, what's happening in terms of the surroundings and what we would expect here because it's exothermic, that the surroundings picks up the energy and becomes more disorder. And we do see that with the positive number. It's only when we put both of those numbers together here that we do get a positive for our delta S of the universe that we can make a determination that the reaction itself is spontaneous. And we would expect this to occur. So again, as I mentioned earlier, just because this reaction is spontaneous, it doesn't necessarily mean that it occurs really fast. It's actually a quite slow reaction, as I mentioned earlier. You do need usually a catalyst here to kind of speed along that reaction to occur faster, but it will occur. And again, that's what spontaneous means. It just means if we leave everybody there, it's going to be a spontaneous reaction. We would expect this reaction to occur. Any questions on any part of that calculation? So sort of the second law of thermodynamics there we were talking about, and here is sort of the third law of thermodynamics. And really the third law of thermodynamics is that the entropy of a perfect crystal substance is zero at absolute zero in terms of temperature. So again here, if you think about it, if you're going to make a perfect crystal, there's pretty much one way you could do that, right? And that means that we would have our Boltzmann equation here, where our microstates would be 1, again making this 0, and thus giving us a S value of 0 in a perfect crystal situation. Here's just sort of a entropy sort of curve, if you will. Based on what we talked about here, we see that in our solid state, as you can see in this picture, everything is very ordered and arranged really well. There's a lot of order. And as you can see here, we have a lower entropy value. As we get into the liquid state, again, relatively ordered, a little bit more room for movement, and we start to see our entropy value increase. And here, obviously, when we get to our gas state, everybody is flying around. We also see here something that we'll talk about later in this chapter as well, but these are plateaued. So this is kind of like a heating and cooling curve, just kind of up on its side there. And remember that transition between solid and liquid, if you remember, as you go from, say, solid to liquid, there's a certain amount of heat required to do that, and that's the delta H of fusion. And that's what we see here. This is the delta S of fusion. It's that entropy change that occurs at the same temperature at that plateaued part. And it describes the entropy change that occurs as you go from solid to liquid or backwards. And that's the delta S of fusion. And same as we've been talking about, if you're going from solid to liquid, you're creating more disorder, more positive number, more negative if you're going the opposite direction. Same thing with as you go from liquid to gas, right? That is the delta H of vaporization that handles that transition. And the same thing occurs here. We have a delta S of vaporization, which is the process as it goes from liquid to gas or backwards. Again, a positive number as we go from liquid to gas, more disorder, a negative number as we go from gas back to liquid. And we'll talk a little bit more about that later on in this chapter as well. Any questions on entropy? So entropy disorder, again, a couple of different things with entropy as we talked about. First off, the unit. So typically when quoting units for entropy, it is joules rather than kilojoules. And again, you'll find some values for those things in their standard state that you typically won't for things like delta H. And again here, when we increase the disorder, we actually become more positive. When we decrease the disorder, we become more negative. And we do use our delta S of universe to figure out whether or not a reaction is spontaneous or not. Any questions on any of that there? Okay, so I think it's a good place to stop, probably a good stopping point. So coming up on Thursday is our exam, right? And that is on 14 and 15. So we'll do what we done before. We'll have a short little lecture on this stuff, and then we'll stop a little bit early, probably in lecture, and then during lab time, the exam will open, and you can take the exam, obviously using proctorial and all that stuff like before. In terms of lab today, we're going to do one more day here of buffers. So we kind of talked about it. So again, you can use that time to work on the buffer experiment and the calculations and submit your calculations and get them looked at and stuff like that. So that's what we have on tap for today. Other than that, if there's no other questions, I'll see everybody in about 20 minutes or so. Make sure you put here if you haven't done so already.